We want to evaluate the line integral of xy squared along the curve C with respect to arc length, where C is the right half of the circle given by x squared plus y squared equals 16, which is graphed here. Notice how we have the right side of a circle centered at the origin with a radius of 4. Because the integrand function f of x comma y equals xy squared is non-negative along this path in the xy plane, the value of the line integral does represent the area bounded below by this curve in the xy plane and bounded above by the integrand function. Let's look at this graphically. So the integrand function is graphed here in purple. We're integrating the purple function along this curve here in the xy plane. And again, because the purple function is non-negative along this path, the value of the line integral does give us the area bounded below by the curve and above by the purple surface, which should be the surface area on this green cylinder here and here. Notice how I've also graphed the corresponding curve that would be on the purple surface so you can better see the area we're finding by evaluating the line integral. The line integral is going to give us this area plus this area here. So going back to our work, we need to begin by writing parametric equations for this curve in the xy plane. And because it's a half circle with a radius of 4, let's let x, or x of t, be equal to 4 cosine t. And let's set y, or y of t, equal 4 sine t. Now let's determine the interval for t that would trace out this curve. Let's say we want to start here at this point and integrate in this direction. This would be the orientation of the curve. Well, notice when t equals 0, we'd be at this point here, 4 comma 0. So if we want to start here, notice how we'll have to start when t equals negative pi divided by 2 radians. And then we'll stop integrating here, where t would be equal to pi divided by 2 radians. So the interval for t that would trace out this curve is t is greater than or equal to negative pi over 2 radians, and t is less than or equal to pi divided by 2 radians. To check this, when t equals negative pi divided by 2, here we'd have 4 cosine negative pi divided by 2, that's 0. And then y would be equal to 4 times sine negative pi over 2, which would be equal to negative 4, so it would be at this point here. Now looking at our notes below, to evaluate the line integral, we need to write it in this form here, where we need to write f as a function of t using our parametric equations, and then differential s is equal to the square root of x prime of t squared plus y prime of t squared dt. Since we already found the parametric equations, let's also find x prime of t and y prime of t. So x prime of t is equal to the derivative of 4 cosine t, which is negative 4 sine t, and y prime of t is the derivative of 4 sine t, which is 4 cosine t. And we also need to write the integrand function f equals xy squared as a function of t. So f of x of t comma y of t would be equal to, well again, x is 4 cosine t, and y squared would be 16 sine squared t. Now we have all the information we need to evaluate the line integral. The given line integral is equal to the integral of, again, f of t would be 64 cosine t sine squared t, and then we have times the square root of x prime of t squared, that would be positive 16 sine squared t, plus y prime of t squared, that would be positive 16 cosine squared t dt. The limits of integration for t are from negative pi over 2 to positive pi over 2. Let's simplify this and then evaluate this on the next slide. Notice here, if we factor out 16, we'd have 16 times the quantity sine squared t plus cosine squared t. Well, sine squared t plus cosine squared t is equal to 1, so this simplifies to the square root of 16, which equals 4, and 4 times 64 is equal to 256. Let's write this as 256 times the integral from negative pi over 2 to positive pi over 2 of cosine t times sine squared t. And now I'll perform u substitution. Let's let u equal sine t, and then differential u is equal to cosine t dt. So in terms of u, all of this, again, cosine t dt is equal to differential u, and sine squared t is equal to u squared. So the antiderivative is going to be 256 times u to the third divided by 3, or 1/3 u to the third, which would be 1/3 sine cubed t. Now we need to find big F of b minus big F of a. So we'll have 256 divided by 3 times, when t is equal to pi over 2, we have sine cubed pi over 2 minus, when t equals negative pi divided by 2, we have sine cubed negative pi over 2. So we have 256 thirds times the quantity. Well, sine pi over 2 is equal to 1, so we'll have 1 cubed minus sine negative pi over 2 is negative 1, so we have negative 1 cubed. So this equals 256 divided by 3 times, this is going to be 1 minus negative 1, or 1 plus 1, which is 2. So the exact value is equal to 512 thirds, or as a decimal approximation, this would be approximately 170.6667. And again, this does represent area because the integrand function is non-negative along the path or curve of integration. Going back to our three-dimensional graph, we just found the area bounded by the purple function along this red curve in the xy plane, which would be this area and this area. Now the way to think of this is if we were to build a fence along this curve in the xy plane up to the height of the surface area of one side of the fence would be equal to the value of the line integral that we just found. I hope you found this helpful.